All right. Good afternoon. I'm Erik, presenting with Hesham today. He will come in a few slides. So what we're talking about today, we had a great intro in the keynotes, right? There's a lot of talk about sustainability, right? How much resources are poured into this, as well as we saw some of the circularity aspects that we're going to get to, right? So I think we're going to kind of dig into a little bit of the details, and then we're happy to answer more questions if there's time or after the fact, right? And so basically, we're going to talk about some of the design choices that were made as part of OCP and how they help the entire life cycle of the systems, right? And so then we're going to talk about some of the footprints of those systems, and then actually what happens with the materials and the details, right? So embodied carbon, right, is a key point. One of my past talks here was sharpening our pencils, right? There's a lot of details that go into the carbon footprint of a server, right? All the materials that go into all the pieces that go into the server. Then there's the running time of the server, there's the workload and so on. So there's a lot of pieces, right? There's a lot of, but it's all kind of understood and you know, it can be reduced to numbers and to spreadsheets and data. And therefore, since we know how to measure it, we can improve it, right? So lots of resources, right? Both materials that need to be brought out of the ground, right? Materials like water that need to be used all the time, but also, you know, precious metals and all these things. But then, of course, at the end of the day, we all want to run our containers on things. Oh, maybe containers are now a bad thing. Oh, I didn't think about that. So what we want to talk about is the design footprint of servers and then racks, right? So let's talk about those footprints, right? So this is you know, discussions that have happened since the earlier days of OCP, right? One of the goals of OCP was to simplify the deployment of large numbers of servers. So that was rack scale integration, so you can just roll in an entire rack. That's why we have bus bars and so on. But a lot of the focus was to simplify and make it easier to service, easier to manage, faster performance. You know, that also led to naturally less materials, right? And so that's what I'm showing here. So here we have maybe a traditional 1U server at the time that OCP or the core systems of OCP were being developed at the initial round of systems. And then on the far side, an OCP server, right? One of the biggest innovations of OCP, right, was that 3 of those servers fit into the same space as 2 of these pizza box servers, right? And so obviously in order to do that, there had to be some material that had to be removed, but the server still had to run, right? And so how was that done? It was done by taking out a lot of the complexity and into fairness, the flexibility that was in these more traditional servers and simplifying it, right? And so it was done in terms of fans and heat sinks and so on. So we'll go through it quickly, one at a time. There's a little table. The CPUs, right, memory, heat sinks, fans. So one of the biggest things that you see here in this OEM server, right, is there's 12 tiny little fans in here, right? Why are there 12 fans? There's 6 fans because they have to go all the way across the 1U, and then there's 12 because they have to be redundant. In case one of them fails, there's a second one, right? So there's literally twice as many as are ever needed, and the only reason that 6 are needed is because the thing is so flat and a fan has to be square, right? So as a result, it means that in a rack, you have 480 of these tiny little fans, right? Half of which weren't even supposed to be important in the first place. What we did in OCP, right? So OCP is 3 servers in the 2U, right? So now you get 1 extra server, 50% more, and the fans are now 2 more larger 2U fans square. So you only have 96 fans in the entire rack, right? And they are, in fact, more efficient at moving air because a larger fan moves more air for the same amount of electrons, right? So it's win-win-win. Less materials, improved reliability, right, because there's still 2. So there's a number of different aspects of that. The same thing happens with, or similar thing happened with heat sinks. Similar things with some of the componentry, some of the drive trays and so on, right? Those servers have, you know, 10 or 12 drive trays, and the average drive the count is 2 or 3, right? So there's a lot of flexibility, but a lot of also overhead. So what we did here is we then summarized at an entire rack level. So there's 4 columns here. One is the per server count and the per server weight in grams of each of these kind of major components or significant components of the system. And then is the rack level, and then the rack level total kilograms, and then finally a total kilogram. So you see that a rack worth of 40 of these 1U servers is just shy of 1,100 kilograms, right? And an equivalent rack full of OCP servers has an additional 8 servers because of the space advantage that we get, and is 720 kilograms. So you're saving almost 400 kilograms, just a little bit over 30%, and you're getting a little bit less than 30% more computing, right? So the advantage is well over 50%, right? And that's pointed out here. So if we look at the cores, right, in the traditional system, it's just about 1 core per kilogram. And if you look in the if you summarize that as a percentage of the total, this was an interesting number when we first put it up. So the core computing elements of this rack are literally less than 2%. So 1.3% of the rack is the stuff that actually does the computing. The rest of it is just support infrastructure for all that computing, right? Bringing in the electrons, taking out the heat, et cetera, right? The OCP system, because of the simplification, because of the density advantage, is almost 2 cores per kilogram. So like I said, it's twice as good in terms of the core efficiency. And we take it up to a massive 1.8% now of the rack material is dedicated to the computing. And we've done better, right? But it's still a very significant amount. So how do we deal now with all these other pieces, right? One aspect we're not going to talk about a lot today, Heshem will briefly mention it again later. When you bring in the storage elements, you get another kind of boost. So then you get almost 5% of the rack if you include both compute and storage. Storage has some other upsides and some other downsides. But regardless, it's still a small fraction. Okay, I already talked about the fans, right? And then I'm going to skip this next one because there's some other aspects, but it's not sufficient in a 20-minute talk. So now, in this next section, Heshem will talk through, okay, now what happens once you have all this equipment? Now you run it for 3 years, 4 years, 5 years. What are you going to do? How can we kind of extend the life and improve the efficiency?
Sure. Thanks, Erik. All right. So I'd like to show you a couple of use cases in terms of the recycle, reuse, reuse space, and putting things into perspective when it comes to actually avoidance or actually emission reduction across the value chain. It's quite significant, and a few notes on that. So a lot of these use cases are actually done today. So we are, as Sims Limited and as Sims Lifecycle Services, we are recycling, we are repurposing components, but we are also repurposing entire racks, basically. And I just want to show you what the impact is on. I wouldn't call it scope free because there's who can claim that it's their scope free if you reuse your component, but let's call it emission lowering or avoided emissions in this sense, right? Now we saw like obviously the reduction in kilogram in weight, specifically on different frames, the rack size with the OCP standard. And let's look at it from component to component, starting with CPUs and DIMMs. Now we've seen today in some keynote talks that vertically integrated companies like OVH, they do it on their own. So they take their DIMMs out, they reuse them. And the strength really of the OCP ecosystem is that you can just like take it out, the sockets, and you can put it in any other socket or server, Broadwell, Haswell server or workstation. Same with the DIMMs. They're DDR4 specified, so it's really easy to take out. So it really enhances the reuse aspect. Now, why is that important? Obviously, internal, external reuse. So this has been done for years already now. So either OVH, who do it on their own, or us, Sims Lifecycle Services, who do it for hyperscalers or others, either reuse it then back to the client or actually reuse and then resell it on the wholesale market. So obviously there's also an economic value. So if you think of a new DIMM, it's about $75, right? And put that in perspective, 5 of these DIMMs have the value of 1 ton recycled ferrous scrap. So there's a significant interest also from an economic perspective to reuse. So to harvest, test, ship it back, or ship it to someone else for reuse. So there's some processing fee associated with that, but basically a couple dollars less, you still have like a really good value from with regards to the market value. However, the most important thing, if you look here, if I just recycle the entire rack, so this is an example, an actual calculation, and putting into perspective also what we know, what it costs to recycle, the energy is used, etc. On the left here, if you recycle the whole rack as is and separate the different components to steel, aluminum recycle, copper, plastics, etc., you get about 1,400 avoided or reduced emissions in that sense. However, if we reuse the CPUs and the DIMMs, but recycle the rest, you see that factor increase in terms of emission savings. Now, that's not insignificant. So how do we do it? We're not going to pick it up with hands, right, manually. And if you've seen the talk today within the startup session, we're partnering with Molk to do it in an automated way. So having really these micro factories, we have a few installed. We're installing more over the next few months to really have a very repetitive process where you push the service into a certain place. I mean, hopefully you've seen the video, but really have then 2 robot arms do the job for us, taking away the cover, taking away all the different components, and returning the harvested server back. So here you see the DIMM pulling, and here you see the heat sink, and then you have a different change of the head, and then removal of the CPU. And excuse me. Now, storage is always a very interesting subject when it comes to reuse, right? You have a lot of the data centers which don't allow any usage or reuse of hard disk drives or storage in general. So we get them bent, we get them already shredded, we get them in some way or form at which we can't reuse. But there is a lot of value to it in terms of coming now from 23,000 tons of kilograms of CO2 saved to around 50 if you reuse some of these SSDs. In the example of the server stack we have here of a particular OCP server. There are ways, to improve recycling nevertheless. So we have technology where we cut the corners and we try to harvest the coil, which has the rare earth magnetic material, neodymium, ferrous boron. So there are ways to improve, especially all these very scarce and high cost and high mining cost associated with high mining cost materials to take them out and get the benefits. But I think it will take a while for us to really reuse a lot of these storage devices. But there's value in it from an emission savings perspective. Looking at other components, heat sinks, chassis, bus bar, rack. Yeah, you can extract the metal. If you just extract these components, excluding all the computing components, you're at a decent number, right? Versus extracting the whole rack. But just to put that in perspective, reuse is still the way to go in terms of being more sustainable. Now, other components such as motherboard, fans, it's not very common to reuse those. We mainly recycle in the motherboards for materials extraction. So getting precious metals such as gold, silver, palladium, copper from these PCBs. But it's not necessarily the cleanest way. You're smelting it down. You have a lot of different separation steps. CO2 intensive, compared to your standard ferrous or non-ferrous recycling streams. But that's the standard right now across the industry. But again, we'd like to reuse more motherboards and, in fact, all other components. Now, can we do better? Yes. We can do all of these use cases here. We're doing them right now, right? But If we reuse all 48 servers as is, and we might need to reconfigure a few, exchange some BIOS chips, BMC chips, add new hard disk drives, because typically we have to destroy them, we get the highest benefit of avoided emissions here. All right. And with this, I think we can
yeah, we can take some
close.
questions.
Yeah.
Yeah, I just want to emphasize the last, one of the things that Hesham just said on this last slide, right? So this is all, what we've talked about today are all things that are being done today, right? So I've been involved in these processes for more than 5 years. You know, Sims as a company, maybe 10 years and 20, 25 years for the full recycling and the industry. So a lot of the major players are doing the simple versions of this, right? The commodity reuse and so on. Right, that we did have a little bit of time, so we did, you know, Hesham did talk the full detail of that storage. If we could do storage devices, that's a big savings, right? Obviously, it's balanced by that privacy concern of you know, what is the data that's stored on these devices. But for any organization that knows, right, what the data is, or they know that they trust in their encryption, et cetera, if you are able to reuse, extend the life of your storage devices, that's a huge additional win beyond just the simple commodity components, right?
And we talked about it yesterday, where, you know, some of these SSDs, they have, they're barely used. So actually, if you look at the write times per day, right, they're, yeah, it's barely used, in the sense that the lifetime could be more like around 20 years potentially. So, but these SSDs in particular, they're just getting recycled, destroyed and recycled. So there could be some rethinking around that as well. So a bit of a cultural change within the industry, which would help it.
Yep. And I think then also the extended life, right? So I think Facebook announced maybe 6 months ago, 9 months ago, that they're taking their average lifetime from 3 years to 5 years, right? OVH, Gregory did an excellent job this morning. They've been doing that for the entire life, you know, the entire 10 years of that company or more. You know, waterfalling their servers, right? When you're hiding a server behind a virtualization infrastructure, you really have no idea how old that server is. As long as that server is serving up your VMs and answering your HTTP requests, it doesn't know what the microarchitecture that's being used in the back, right? So we have a couple more minutes for questions.
Question about the transparency. How the client can understand and confirm that this is the savings on CO2 emissions from his side, from point of view of scope 3 and another. Is there any tool for that, or confirmation or approvals?
Well, we have something on our own, where it's an emissions calculator, where we know exactly how much it costs us to harvest, how much energy we're incorporating, what our partners for example, on the plastics recycling side, what their consumption is, what their energy usage is, CO2 emissions, etc. So we can estimate, and we have a calculator actually, which shows our clients what the reduced emissions is. That's on our side, but on the regulatory side, I think we're still lacking a little bit.
So there's literally a meeting across the hallways, right, where there's a dozen people. There's a significant effort that's probably 50, 75 folks within OCP that are trying to kind of standardize the way some of those things are measured, right? And so it's probably always going to be a little difficult to know, you know, what Samsung or Intel is doing in their factories, right? But there's a lot of incentive, as you heard maybe in the sessions this morning, to you know, explain what that is and just be transparent as you say, right? And at least my positive experience has been, as long as my term in the industry, there's a lot of things that used to be secret that aren't secret anymore, and because they're not secret anymore, we're able to do them better, right? So I think I'm maybe a bit more positive than some of the discussion was this morning, right?
Yeah. No, it would be great also to have a comparison of really the different like OCP components versus proprietary ones, because right now we're relying on manufacturing numbers from eco inventory databases, etc. But you know, some of them are outdated, so we have to modify them a little bit. So there's not yet, I would say, a framework which gives, you know, the full transparency to that.
Okay, we're running out of time. Thank you so much, guys.
Thank you.
Thanks, everybody.